Hello and welcome to this lecture. In this lecture I will introduce multivariate linear regression. Multivariate linear regression takes the idea of univariate linear regression a step further. If you're not familiar with univariate regression, please jump into the 101 lecture on this topic. So what are the similarities and differences between univariate and multivariate linear regression? In both cases you try to fit a linear equation to predict a target variable y. In univariate regression, you have only one independent variable x1, whereas you have multiple independent variables in multivariate linear regression. In the second equation you can see there are xn different variables. In the previous lecture on univariate regression, we only considered one variable, the living size, for predicting the price of a house. Now, with multivariate regression, we take further variables into account, like the age of the house, the quality, and possibly many more. There are a few model assumptions associated to multivariate linear regression. First, the relationship between independent variables and dependent variables should be linear. This could be checked by creating scatter plots of all independent variables and dependent variable. You can see an example on the right side. Black points are actual observations and the blue line indicates a linear regression. Here you can assume that the relationship is linear. You should make sure that your model is homoscedastic. This means the following. If there are certain features in your data and your model does not represent these, there might be a pattern in the error plot. You can plot the error, defined as difference of actual and predicted values versus the predicted values. There should be no pattern in this plot, so the points should be all randomly distributed. Otherwise, you should rework and adapt your model. Another model assumption that should be verified is multicollinearity. Multicollinearity might be a problem if there is too high correlation between independent variables. At the right side you see a correlation plot of 5 independent variables, x1 to x5. In the upper right triangle you visually see the correlation coefficients as circles. The correlation coefficient ranges from perfectly negative correlation, -1, indicated by a red circle, to a perfectly positive correlation, indicated by +1. Negative correlation between x2 and x3 means that if x2 increases, x3 decreases. On the other hand, positive correlation, for example between x2 and x5, means that if x2 increases, x5 increases as well, and vice versa. The lower triangle shows the actual correlation coefficients. To make sure that there is no multicollinearity, the correlation coefficient between two independent variables should be below 0.8, as a rule of thumb. The final assumption I want to present is multivariate normality. This means you should check that your errors are independent. Specifically, you should check that the residuals, which means the differences of actual and predicted values, are normally distributed. You can perform this check with a quanta-quanta or short QQ plot. Such a QQ plot you can see at the right side. It shows the residuals and compares them to a normal distribution. Multivariate normality can be assumed if the residuals mainly follow the straight blue line. In the next lecture you will see some interactive dashboard with which you can play to get a better understanding of the topic. So stay with me for the next lecture. That's it for this lecture on multivariate linear regression. Thank you and see you in the next one.